Hi everyone, we are back again with a new video. Today I try to speak in English, but it's not my language, so it's a challenge for me, but it's also a test for me. So today we're talking about shear force and bending moment acting on a wing. In the first representation that is indicated from two black arrow, we have a simple representation of a beam with the uniform load of amplitude equals to q. The length of this beam is equal to half span, so this is the half span of the wing. On the figure number 1, instead we have the same wing but seen from the cross section. So if the first representation is the wing seen from the front, the figure 1 is the wing seen from the cross section, and we see an airfoil with the body reference line that is indicated from the acronymus BRF. On wing acting the well-known forces that are lift and drag, and the summation, the vectorial summation of these forces give us the aerodynamics force that is indicated with the F in yellow. This airfoil has an incidence indicated with the EV/EW, and the free stream velocity has an angle with respect to body reference line of indicated with alpha I. So the alpha final, the real angle seen from the airfoil or the wing is calculated with this equation, that is alpha final equals to alpha initial, that is this, plus EW, that is the incidence of the wing. So if we move on, this representation, figure 2 is the simple zoom of this reference frame, that is y and x for the airfoil. We can call this epsilon y a and x a. Epsilon is y, x is x in English. So this is the figure number 2, that is the zoom of the reference frame seen before. We have here the lift force acting on the airfoil and the drag force. So if we projecting this force on the normal direction that is represented from the y axis, we can calculate dy and ly. In Italian is dy ly. But there are many angles here. Alpha F is alpha final, that is calculated with this relation, alpha initial plus incidence of the wing. But the other angles, so in the question number 3, we have the calculations of the angle gamma and epsilon. Gamma, that is this angle, is calculated as the pi over 2, that is 90 degree in radians, minus alpha final, because this in red is 90 degree, this in blue is alpha final. The difference between these angles give us gamma. But epsilon instead is equal to 90 degrees again minus gamma angle. But gamma angle is equal to 90 degrees minus alpha final. The summation, the arithmetic summation of these quantities give us that epsilon is equal to alpha final. So the angle between L and Y, that is the normal direction, is equal epsilon, but epsilon is equal to alpha final. The angle between D and X direction, this is parallel direction, is equals to alpha final. So we can calculate dy as D times sinus of alpha final, and while Ly is equal to L times cosine of alpha final. But we can express this formula in a non-dimensional unit, so we can reach to the formula expressed in formulas expressed in the relation number 4, that CDY is equal to CD, this is the local CD acting on the airfoil, this is the 2D CD, times sine alpha final, CLY is equal to CL times cosine alpha final. The combination of these two quantities give us the normal coefficient, local normal coefficient, that will be very important for us in the next part of the video, when we will calculate the local span loading and the local load on acting on the wing. So Cn is equal to summation of CLY plus CDY, but CLY, CDY are represented are listed in the equation number 4. Alpha final is the sum of alpha initial plus E wing, so is the incidence of the wing. So the Cn is so calculated. So we move on a general beam case. So in this case we have a simple beam. No, not think about of a wing. How we calculate the shear force diagram and bending moment diagram? In this simple way, we can substitute the uniform distributed load as a lumped load that we call it Q up in uppercase, Q up, and is equal to Q lowercase times B over 2. That is the span, the length of this beam. So if you remember, this is a simple area of the rectangular shape. If we apply the simple equation of the mechanics, structural mechanics, we can calculate the moment applied in point A and the reaction, the vincular reaction of explicated from the interlocking. So we have MA equal to Q uppercase times B over 4, because this is the half of half B over 2. So B over 2 times 1/2 is B over 4. And the VA is equal to the opposite of Q. So VA is equal to minus Q. Here we have a simple representation of a convention to represent the shear force diagram. So in this case, when the force acting on the X portion of the beam is directed from up to bottom, and the force acting on the left of this dx, this elemental portion of the beam is acting from bottom to up, we have a negative shear. Instead, in the opposite convention is the arrow are inverted. So if we it's simple to calculate this diagram, but we can express the t as a function of x, that is the length of a certain portion of this beam. T of x is equal to integral of q, that is the load, but we must remember this other convention. So this is the important convention for the general beam case. The direction represented from y plus is positive for all the forces directed as y plus. But instead, the direction represented from x plus is the positive direction for all the forces that follows this direction. So q is directed as y plus, so q is positive for me in this convention. So we can write t, the distribution of the shear force, t as a function of x, is equal to integral of q times integral variable, that is the x. This is equal to q times x, because q is uniform, is constant along all the wing, or the beam in this case. So this is equal to q times x plus a certain constant c1. This case is constant, so I don't report q as a function of x. It's constant, so q can exit from the integral scene. Make some calculus. We obtain the equation q times x plus c1. c1 is the constant related to this integration. So if we move on the equation of the bending moment, distribution of bending moment as a function of x, we simply should treat shear force distribution as a function now of x, because we obtain here a linear equation. So if you see the diagram, we can note the element of the trend of this diagram is linear. So it's simply to obtain this diagram. If I put here a section of this beam, here acting this force that is VA. So in response to this VA, I can put here another force, a dummy force. So it's a dummy force. These two forces, VA and VA prime, generated this convention that is a negative shear. So we obtain this. How you can see, I dashed the diagram. This dashed diagram is the shear force diagram when we have two uppercase. In this case, we don't think a load as distributed along the beam, but as a lumped load. So we have this shape dashed here, but we have a uniform load Q, so the diagram is this. The shear is equal to Q at point A and decrease linearly since to B, where the shear is 0. So, I was saying before, this is the equation to obtain the bending moment distribution along the beam. It's the integral of the shear force tau in function of x, and now we know why, times the x. If we integrated this quantity, we obtain q times x squared divided by 2 plus c1 times x plus c2. We must determine the c1 and c2 constant. We have so boundary conditions that m in x equal to 0 is equal to q times b over 4, while in m evaluated in b over 2, so in half span, or just in point B, is equal to 0, how we can see from the diagram. So if we make some calculus, obtain C2 is equal to Q times B over 4, how we expected. So this is C2 is the constant C2 is equal to MA. This is MA, the moment acting in the interlocking, so in point A, in boundary A. While if we put B over 2 in these equations, we obtain, after some calculation, simple calculation, that C1, the other coefficient, the other constant that must know to can express the equation of the bending moment, is equal to minus Q, that is equal minus VA. So at least we have the formulas at number 7, which tell us the shear, the distribution of the shear along the beam, along the x coordinate, is equal to Q times x, so is the load times x, which is a portion. X can be this. We know the shear at x, for instance, to 2.2 meters, for instance. Minus Q is, we see, is VA. So Q times x minus VA is equal to give us the distribution of the shear force along the beam. Mx is the distribution of bending moment, the equation of the distribution of bending moment along the x coordinates. That is equal minus Q times x, so is minus VA times x plus the load times x squared over 2 plus MA. This is the C2 constant. And the formulas expressed in equation 7 is much simple. You can see if I have a linear, for instance, a linear distribution of the loads. So if I have something like this, that is quite similar to the distribution along a real wing. In this case, the wing can express it as a sharp tip. It's possible, but this is taper ratio equal lambda ct over c root equal to 0. So a similar distribution of load is this. This is wing. So here, if I have this, I must calculate for the T, the distribution of the shear force along the beam, now not is more constant, but is linear. So I must know the equation of this distribution. So I can calculate this distribution. For example, here is Q1, here is 0, so at x1, at x1 equals to 0, we have y1 equals to Q1. At x2 equals to L, for instance, we have x2 equal to y2 equal to 0. Now, apply the well-known formula. We can calculate x minus x1 divided by x2 minus x1 is equal to y minus y1 divided by y2 minus y1. We substitute the value reported here, highlighted here. We have multiply in cross direction, so these for these and these for these. We have minus q1 times 6 equal to y times L minus q1 times L. Solving for y, we obtain y is equal to minus q1 times x plus q1 times L divided by L, we obtain finally minus q1 times x over L plus q1, and this is the equation to put in the integral. So tau t of x, shear force distribution, is equal to this equation, minus q1 times x plus q1 dx. So this is equal to minus q1 times x squared, here is divided by L plus q1 times x plus c1. But c1 now is simply to calculate, because if I put here a lumped force q that is equal to q times q1 times L over 2, that is the triangular area formula, we obtain that c1 is equal to minus q. So this is equal to minus q times c squared over L plus q1 times x minus q. It is simple to calculate t in function of x, because x equal to 0, we have minus q1. T when x is equal to L, we have a certain value. So here I missed the 2, quindi, so we have minus q1 times x squared over 2 times L. When I calculate t as a function of L, we have here minus q1 L over 2 plus q1 times L minus q1. This is equal to a certain value, but as we can imagine, this is equal to 0, because this quantity is equal to q1 times L over 2 minus q1, but this is q1 minus q1, which is equal to 0. So this is a simple method to calculate the shear distribution on the wire. For exercise, we can make some calculus for obtain the distribution of bending moment along the beam when the load is not more constant but is linear, starting from this equation of the load and this equation of the distribution of the shear force. So now move on the focus of this video. We have been explored some details of the calculus for this beam when the load is constant, when the load is linear. But in a wing we have a quasi-elliptical distribution that is no linear. We can see, I hope, this dashed line that is the load, uniform load along the beam, and is not so linear, because if I make a line here, so in this way, I miss this area. I lost this load that in real case there's this load. In this, with this approximation of linear, this load I miss it. So this is a quasi-elliptical distribution because the weight, because the wing is not elliptical wing, but is a straight tapered wing. So in the load, typically the load is this for a straight tapered wing. One of the motivation, because the wing has a taper ratio. So a taper ratio again is lambda, the ratio from between the chord to tip divided by chord to root. Is motivation is we would obtain a distribution of load elliptical, and we know that an elliptical distribution of the load means less induced drag. So in the elliptical wing, we have the minimum induced drag possible. So, but in this case, we can refer to a certain software that calculates for us the distribution, although for the CL. So all this discussion made before is now important, because we obtain the distribution of CL along the wing. The distribution of CD along the wing, we can recalculate the normal coefficient, and when we obtain the normal coefficient, we can calculate L as a function of Y, because we know that in a wing the coordinate along the span is Y, the other coordinate along the fuselage is X. Okay, L as a function of Y is equal to Cy times Cn of Y times Q. Q is the dynamic pressure. Q is equal to 1/2 times rho times V square. Rho is the density. So international system is expressed as kilogram over meter power of 3. This is a speed that in international system is expressed as meter over second. The output is in Pascal, which is equal to Newton over meter square. If I put this formula, Cy is the chord at station Y. For instance, this station Y1. So we obtain meter. This is a dimensional analysis. Times Cn is non-dimensional. Q is equal to Newton over square meter. This is equal to Newton over meter. That is a load, span load, local span load. We can do this calculation for every chord of our semi-wing, half wing. In Italian we say semi-ala, but in English is half wing. And we know the distribution of the span loading that is depicted in red in this draw. This is the Ly. Okay, Ly. Now move to see an example obtained from ADAS. ADAS is a software developed by Professor Fabrizio Nicolosi of the University of Naples, of the DAF, the research group of the in the aeronautical flight mechanics of the University of Naples. Now I open an Excel. So we switch in Excel. I can show you all the output of the ADAS, but after I will give you some other reference on ADAS, show you the developer of this software. But this is a wing similar to the ATR 172. With this ETA is the non-dimensional station along the semi-wing, so half wing, so-called half wing. We have all this output. This is the shear calculated from the software, bending moment, and also as here we have the torsion moment. But now we skip this moment. Here I have been calculated the dynamic pressure expressed in Pascal, but to obtain Ly as kilogram over meter, I divided for the constant 9.81, that is gravitational acceleration. This is the CFN, so the normal coefficient in the normal direction, which is this, for if you remember from this graph in the figure number 2, in the y direction. So here I have all the no incidence. E wing is equal to 0, so I have only the alpha, because if you keep in mind this formula, alpha final is equal to alpha initial plus incidence. If incidence of the wing is equal to 0, we have alpha final is equal to alpha initial. Alpha initial in this case is 15.5 degree. So E4 is the cell. So CFN is equal to, in this case, E4 is the cell contain the CL tot, that is the summation of additional CL, the additional distribution of load. You have additional and basic load in a wing. This is the sum of this CL add plus CL pass, basic load. And the other component is CD. That here is represented as a C indacid, because the CD naught, the parasite drag of the wing, is quite similar, less or more, and the calculation so is made with the CD induced, and so this is the CFN that is different from the CL tot. This is the CL along, let's say, the normal direction. The coefficient that is useful for us for our calculation of the shear force and bending moment. So the span loading calculated, as said before, in kilogram over meter is the product of CFN times Q, that is pressure, dynamic pressure, divided by 9.81 to switch in kilogram over meter square, times the local chord, that is 2.5775 meter. And this is along this column we have the Ly, that is this graph. So we have quite similar, but in final we have 0. The last station, that is 13.53 meters, if I remember, is 0. So this is non-linear, is non-uniform distribution, but is a thing like this, no this, but this one. Okay. So obtained this distribution, now we can calculate the shear force that is calculated here. So the summation, let's say a thing, Ly is the local load. So this quantity is expressed as kilogram, and is in this case the trapezoidal approximation. If you see this formula is x4 plus x5 times the difference t5 minus t4 times 1/2, who are these quantity? The first one, x4 and x5, are the local span loading, and which is the if we switch on one note, we have something like this quantity and this quantity, or this station and this station, epsilon 1, epsilon 2, and this is my trapezoidal approximation. This is the Q1, this is the Q2, and this is the height of Q1 is the major base of the trapezoid, and Q2 is the minor base of the trapezoid, and H is represented by this differential of the is represented by the differential of these two quantity, these two stations. So H is equal to y2 minus y1. B major is equal to Q1, B minor is equal to Q2. The area of the trapezoid is equal to B major plus B minor times H over 2. And is exactly this. Okay? So we obtain the local chord, the local, let's say, load as this approximation, because we have seen before that if we have this, we have a rectangular shape, the lumped load Q is equal Q lowercase time L, where L is this. And this is the area of the rectangular shape. If is linear, lumped here, Q is equal to Q times L over 2. Where this is the formula of area of triangular shape. This is the same thing. If the area of this give us a Q lumped of this trapezoid, lit trapezoid. If I divide this distribution in many trapezoid with a certain delta y, that is the step, I can obtain this. Ly, and I can plot this in function of y, but isn't our scope in this case. Shear is calculated as the summation in point A. This is the point A. The first cell represents point A. The last cell of this column is point B. The summation of all these quantity, of all the ellipsion, clearly give us the semi-lift, or the lift acting on the semi-wing, half-wing in this case. So here there's another consideration to do, that there is taken in account the n, that is load factor, where L lift is equal to n times W, and in this case is equal to 2.5. So we can make also calculus for the load factor for n equal to 1, but in this case I presented this example. So the first quantity is exactly the summation of all these, because at point A we seen that if we substitute the distribution of the load as a lumped load as a sum of all the little trapezoids, the sum of, so I mean we have another trapezoid here, 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 and so on. All the load that I can calculate, the summation of this is the Q, this Q, okay? And VA is this, VA is equal to minus Q. So here in this Excel I plot this convention because the shear distribution along the half wing is equal minus Qx dx, okay? But if I following my first convention, all this quantity should be negative, but in this case it's positive, but I changed the convention. So the order is the sum of the VA plus the local load. If this is first L1, L2, L3, and so on, I have this. The shear at station Y2 is equal to minus VA plus L1. We can write this. The shear at station Y3 is equal to Y2 plus L2. But Y2 is equal minus VA plus L1 plus L2. And so on for the order T. And so can you see this? And so we can calculate this the shear, that is all these, and last cell represented the B, the point B of our beam, or the tip of our wing, and we see that is clearly 0. The distribution, so the shear along the semi-span is this. So here there's a comparison from the ADAS, that is the distribution of calculated from the software, and the shear calculated as the trapezoidal approximation. You can see that the two lines, the distribution match equally. Here we have a simple representation of only the shear, the distribution of the shear force calculated, calc shear. This is the approximation. We see that is quite similar to a distribution of a uniform load, that is linear since a certain point, let's say since to 8 meters. From 8 meters to 13.53 meters, the distribution is quite parabolic. So, because in this case we don't have a linear or a uniform load, but it's a quasi-elliptical load. So, since 8 meters, you can see that the approximation can be match the uniform load from the 8 meters, uniform but linear in this case. From the 8 to 13.53, the approximation is no linear, no uniform. But it's a simple, we split this from 8 to 13 meters as many little trapezoid that that the summation of the load generated from the single trapezoid give us the load acting in this little portion. So the bending moment, here the distribution is calculated also as trapezoidal approximation, and we start from the bottom. So in this case from the point B. In point B we have 0, because the load there is 0. Here, how is calculated with the trapezoidal approximation, but who are the members in this formula? Now this is the shear, because we have seen that moment is equal to integral of the shear distribution times the x, but that is in the continuous. We have now we stay in a discrete system. We have many points, many stations along the semispan. We have this shear at any station. The station are these, represented by this column here. So this is the station at 13.53 meters, the tip. So the first term is the shear. So B major plus B minor times the height of the trapezoid, that is in this case the step delta y, that is calculated as the difference from tip station minus the previous station in direction of the interlocking. So we as said before, we are starting from the tip to the root. So T105 is the tip, T104 is the station in front of the tip, the first station in front of the tip. I changed it all, but we can. This is the bending moment at the station 13.46 meter. At station at the tip, the bending moment is 0. How I calculate the moment at the station 13.33 meters? As made before. Now we have the summation of the previously moment plus the trapezoidal approximation. So, as made for the shear, now we have these. I make some arrows to represent the shear. So, here is 0, T1, T2, T3, and so on, Tn. The moment here is equal to, in T2, the moment in station 1, now we starting from here, y0, y1, y2, y3, yn. The moment in y1, y1 is equal to, this is the approximation, is this, t y0, in this case the measure base, B major, in this case B major is equal to T1, B minor is equal to T0, but T0 is 0. The step H, delta Y, is equal to y1 minus y0. So we have B plus B minor times H divided by 2. And this is T1 minus 0 times y1 minus y0 over 2. My2 is equal to the previous moment. So this moment calculated now, my1 plus this. And we have, in this case, T2 minus T1 times x1 minus x2 over 2. And this is the moment at station y2. So on, my(n) is equal to my(n) minus 1 plus Tn plus 1, Tn minus Tn minus 1 times yn minus 1 minus yn divided by 2. So this is the moment ma, because this is the is summation, so the moments in A is equal exactly the summation of these. So this is the equation of the moment at interlocking. So of this quantity from station n1 to k minus 1 in this case. So we have in this case the moment, but we calculated in Excel the distribution of moments following this equation. First the m in epsilon 1, then m in epsilon 2, m in epsilon 3, and so on with this simple formula. The previous moment plus the moment obtained at local station approximated with the trapezoidal approximation using the shear force and the delta y, that is the step. We calculated the moment. So along this column, we have the distribution, the moment at each station, at each y. This column here, the column AA, and this is the moment at interlocking at the point A. The comparison with ADAS is making an error percentage error with respect to ADAS of the 0.002. That is 0.2%. So it's very, very, very low. And this is the distribution of the moment that is appear first. Bending moment calc is not approximation with the trapezoidal approximation, but is calculated as single load respect a certain point, which is the summation of single moments. So in this case, bending moment calc is quite more difficult because is obtained simply that as without trapezoidal approximation. This is VA. We must know where applied the Q lumped, that is the summation, if you remember, of all local load, of this all local load, but the distribution is not linear, is not uniform, but is quasi elliptical. So this X is generally X 0.43 to 0.46 of V over half. This generates the MA, because MA is equal exactly to Q times X. The traction fiber is under the beam, so the moment is positive in this case. Q times X give us MA. So I have here epsilon 0. Now the local load L1 is placed in epsilon 1. If I want to calculate moment in epsilon 1 is equal to MA minus VA times epsilon 1. If I want to calculate moment, for instance, in epsilon 2, where applied the local load L2 at epsilon 2, I can make this. M epsilon 2 is equal to M epsilon 1 plus is equal to MA minus VA times epsilon 2 plus L1 times this portion, that is in this case epsilon 2 minus epsilon 1. So it's more complicated. And for doing this for all local load, we arrive to tip where the moment at the tip is equal clearly to 0, because it's the summation of all these moments acting along the acting along the beam. But this method is quite difficult, and the approximation with trapezoidal approximation is the green line match the bending moment calculated as ADAS, bending moment calculated as this method, but is very crazy. But the trapezoidal approximation is much simple and give us the same result, as you can see. I hope that this lesson is quite clear. Clearly my English is not perfect. I said in starting of this video, this is a test for me, but is also a challenge for me to describe some technical concept in English. Now I switch in Italian to conclude this video. For the English user, we'll see at next video. Bye. And for the Italian, grazie per aver seguito questo video e ci vediamo al prossimo.